Hello and welcome to acceleration. This is an important concept because we've talked already about displacement, we've talked about velocity, and although this picture shows a speedometer, not a velocitometer, if we said that the car or whatever the speedometer was measuring were to be traveling in the same direction and maintaining one direction, we could look at this as its velocity. But if we want to change the velocity of something, what happens? That's basically what acceleration is when we start to change velocity. So we're going to talk about that, what acceleration is. We're going to look at graphing acceleration. We're going to look at constant uniform acceleration. And that's where we'll be starting. And we're going to look at the relationships between acceleration, displacement, time, and velocity. So let's start with average acceleration. Average acceleration we can denote with little a and then a AVE for average in subscript after it. It is simply the change in velocity divided by the change in time, how much time it took for the velocity change to take place. So just like velocity is equal to the change in displacement over the change in time, acceleration is equal to the change in velocity over the change in time. And you know from previous convention that a change in velocity is going to be equal to the final velocity minus the initial velocity. The change in time will also be equal to the final time minus the initial time. Now dimensions, I dare say you probably can guess what they are going to be. If I know that the change in velocity, those units are going to be meters per second. That represents the units for change in velocity. My time units, the change in time, will be in seconds. So when I go ahead and look at this, this is going to be meters per second, or meters per second squared. So acceleration is always in meters per second squared when we're using SI units. So acceleration, just like displacement and velocity, it has both direction and magnitude, right here, direction and magnitude. Remember, displacement had direction and magnitude, and velocity has direction and magnitude, and acceleration also has direction and magnitude. Those are important to remember. This is a little side note. Deceleration, sometimes people will use that term, decelerating. That is not actually a term that is used in science. In science, there is no such thing as deceleration. It's negative acceleration. So it's acceleration with a negative magnitude. That's just a little side note. When we start to graph acceleration, we're going to be graphing velocity versus time. So you remember the graphs that we looked at before. We were graphing position versus time or displacement versus time. That gave us a line that represented the velocity. Now we're going to take that velocity, a little more complex idea, graph that against time and try to understand the acceleration that is taking place. So when we look at this graph right here, there's a few points. Let's look at these flat places first, right there. This flat spot and this flat spot, is there any increase or decrease in the velocity here and here? No. So is there any acceleration? No. When the line is straight across like that, as time goes on, there's no change in velocity. Therefore, there is no acceleration taking place. What about here? There is acceleration taking place here. We have a change in velocity as I'm going along with my change in time. That change in velocity is positive. So this is positive acceleration right here. Right here, I have a change in velocity. It's a negative change in velocity. So it is a negative acceleration over time, as is this negative acceleration. So that is how we can look at this. If this were an object, we would know it's accelerating positively in that direction. It's standing still here. Here it's negatively accelerating, slowing down. Here it's standing still at rest. And here it's negatively accelerating again. Here is an overview of different graphs, and I thought this is an important review, and just to put them all together in one place so you can compare and contrast all these different graphs. In this column, all of these graphs are position versus time graphs. So we have displacement on the y-axis and time on the x-axis. Each one of them is representing a different kind of motion. When we have an object that is, there's no change in its position as we go further in time, it's stationary. So this is a stationary object. Here we have an object that is, its position is changing over time. It's uniform motion. It's consistently changing over time at the same rate. Here, when we're looking at the position versus time graph, this object is accelerating. It is exhibiting motion with constant acceleration. These graphs right here are all velocity versus time. And remember, we just learned that the velocity versus time is going to tell us about the acceleration. When we have time marching on and there's no change in the velocity, well, and the velocity starts at 0 and it's still at 0. This is showing it's a stationary object. Here we have no change in the velocity, but it has a velocity. It's not 0. This is uniform motion. Here we have a change in the velocity over a change in time. So here we have motion with constant acceleration. These are graphs of acceleration versus time. What is happening to our acceleration as we go on in time? Here, there is no acceleration at all over time. This is a stationary object. It actually looks the same as what a uniform motion would look like. There is no acceleration at all over time, and there is no, it's starting at 0. When we have acceleration happening, constant acceleration, the graph would look something like this. There is a value for the acceleration and it's constant over time. So if we know that an object is moving with constant acceleration, how can we find its displacement? There's a question I'll put to you. Let's think a little bit about this graph here. We have velocity versus time graph. We have constant acceleration going on right here. Remember that, let me go ahead and write our formula down. Average velocity is equal to the displacement or change in position over the change in time. In order to know our average velocity, we just need to remember what average means. When you find the average of something or the mean of something, you know from math that if we have an average velocity, let's say we actually know our initial velocity and our final velocity, and we take those 2 points. That's 2 different points that we have values for. You'll remember from math, to take an average of 2 values, you would add them together and divide by the total number of them, which are 2. So I take the final and the initial velocities divided by 2. That gives me the average velocity as well. When I look on my graph, just to give you a visual of that, if I have constant acceleration, my initial velocity and my final velocity and my average velocity should all be equal. So these values are all equal to each other. And so I can manipulate the math here really nicely to get a very nice equation on how we can find displacement. So all I did right now is, if the average velocity is equal to my definition that we all talked about, the change in position over the change in time, and if I know that average velocity can also be equal to this value, then these 2 values must be equal to each other. And so I just set those up equal to each other. I said change in position over change in time must be equal to the change in the final velocity plus the, not change in, final velocity plus initial velocity divided by 2 for the average velocity. Once I do that, I can simply do a little algebra, multiply both sides by delta t. And when I do that, these cancel out, and my final equation would look like this. The change in position is equal to, I just pulled this 2 out to make it 1/2 times the sum of the final velocity and the initial velocity times delta t. And that is my equation. And on the next slide, I will have it written out neatly for you. And there it is, the equation for displacement when we have constant uniform acceleration right there. And you are very capable of deriving that yourself. If you're out in the middle of nowhere and you really need to know this equation, you have the tools to come up with that on your own. Another important point to let you know about, if you're reading other textbooks, sometimes other physics equations or from other sources, this convention, it's a little subscript 0, means the same thing as this little subscript I, initial. So if you see V0 is what you would term it, it means the same thing as the initial velocity. It can be used with other variables like time. T0 means initial time. So just something so that you're aware of in case you come across that. Now let's try a little example here. Let's say you are driving along in your car at 75 kilometers an hour, and you know there's a stop sign ahead, so you know you're going to need to stop. You begin to brake. As soon as you start braking, you're causing your car to uniformly negatively accelerate. You achieve a dead stop in 6.0 seconds. How far did your car move while you were applying your brakes? So let's start and write down the things that we know. Okay, I know my formula from the previous page for displacement with constant uniform acceleration, because we have constant uniform negative acceleration. So this is the formula I can use. And the variables that I do know, I know my initial velocity, I'm told is 75 kilometers per hour. My final velocity at the stop sign, I know is 0. My change in time, it took me 6 seconds to get there, so it's 6.0 seconds. Now, there should be a big discrepancy that jumps right out at you, and it's the fact that these units do not agree. We need to get the velocity in meters per second. So let's set that up right now. Okay, so when I start with 75 kilometers per 1 hour, I can convert these hours into seconds, and I'm going to convert the kilometers into meters. I know that 1 hour equals 60 minutes, so my hours cancel. I know that 1 minute equals 60 seconds, so my minutes cancel, and I know that 1,000 meters equals 1 kilometer. My kilometers cancel out, and I am left with 21 meters per second, because my only units left were seconds and meters, and I went ahead and said 75 times 1,000 and then divide that by 60 squared. I get 21 meters per second. Now, this is not my answer. This is simply my initial velocity. So if I take that initial velocity and I plug that in, so that's what I just converted that into. Plug that into my equation, it should look something like this. When I plug all those values in, I have my delta x equals 1/2 times my initial velocity of 21 meters per second plus my final velocity of 0 meters per second, and my change in time is 6.0 seconds right there. When I multiply all that out, I end up with 63 meters. And if you look at this, the units right here are going to be in meters per second. So the second here for the time cancels out with those seconds, with that second in that unit, and we're left with just meters. So my displacement, how far my car moved while I was negatively accelerating, is 63 meters. So we're going to look at two more useful equations when it comes to constant uniform acceleration. And the first one, I'll just give you the equation up front, and I'm going to show you how I get that equation. Let's say I would like to know my final velocity. Well, I have all the information I need with all the equations I have, and I'm going to show you how we end up deriving this. Let's start with what we know. I know that acceleration equals change in velocity over change in time. I can write that a different way. I can say acceleration equals final velocity minus initial velocity over change in time. I haven't said anything new so far. We all know this. I can try to isolate that final velocity variable. And in order to do that, I would probably like to multiply both sides by change in time. If I do that, the change in time cancels on the right side, and I end up with acceleration times change in time on the left, and simply final velocity minus initial velocity on the right. Now, in order to isolate again that final velocity, I can simply add initial velocity to both sides. When I rewrite that, I simply get the initial velocity plus a times acceleration times change in time equals final velocity. That is the same as this equation, just the two sides reversed and flipped around. So you already have everything you need to know to solve these problems. You're simply rearranging the equations. Now here is a useful equation, another very useful equation for displacement with constant uniform acceleration. This displacement, however, is written in terms that do not involve the final velocity. So if you have, for some reason you need to know how to calculate the displacement, but you don't know the final velocity, you can use this equation. And again, this equation simply comes from the previous two equations we have just derived for ourselves. Here are those two equations. Here is our displacement with constant uniform acceleration. It involves final velocity, however. This one is our final velocity when we're looking at constant uniform acceleration. And we can combine these two equations by substituting. We know that final velocity is equal to this. Therefore, that final velocity could be substituted with that large term. So let's go ahead and plug that in and work the algebra out. So I plugged that value in, and I wrote this in green. I wrote it right into there in green, so you can clearly see what I'm doing. So now I have the displacement equal to all of this, and I no longer have a term that is the final velocity. So if I don't know the final velocity, this is a really nice equation to use. I'm going to go ahead and combine these initial velocities and rewrite the equation here to two initial velocities. And I went ahead and combined a few steps. You can go ahead and work through this yourself, but when we are looking here at the delta t needs to apply to all of these in the equation. I forgot to add that in. So we end up with two initial velocities times delta t plus a times delta t squared. And when I take half of all of that, these twos end up canceling out, and I get my displacement equals all of this. And I just went ahead and put parentheses around that. It's the delta t squared, not just the t, but the entire delta t is squared. So that should have parentheses around it there. I apologize for that. So you are able to derive this all yourself. Again, in case you're lost in the woods somewhere and you don't have your physics book with you, you can come up with this formula all on your own. Now let's do a little practice with this. Let's say that you are sitting in your airplane waiting to take off on a vacation to Cancun, and you wonder what your takeoff speed is going to be. Your plane is sitting at rest, and then your pilot gets on the speaker, like, you know, he always does, right? I'm sure this would happen. And he tells you that you're going to undergo a uniform acceleration of 5.0 meters per second squared until takeoff. So you time this time of uniform acceleration, and it comes out to be 13 seconds. What is your speed at takeoff? Let's look at what we know and write that down first. I know that my initial velocity is 0 meters per second because I'm sitting at rest. I do not know my final velocity. I would like to know that, right? What is your speed at takeoff? Acceleration, the captain told me it's 5.0 meters per second squared, and my change in time I found to be 13 seconds. Now, when I thumb through my equations that I can use when I'm looking at constant acceleration, I find this one, to be the most applicable and the most useful in this situation. So I can simply start plugging values in. I do not know my final velocity. That's what I'd like to know. I do know my initial velocity is 0. I know my acceleration is 5, and I know my change in time is that. And when I actually plug and chug, this kind of problem is pretty simple. My final velocity is just 65 meters per second. I'm limited by 2 sig figs in all of these, and my units match up, and that is the speed that I'm going at takeoff. Now here's another question. If you know, while you're sitting there waiting for your plane to take off, that the runway is only 412 meters long, are you going to have enough runway for your plane to take off? Well, I actually have 2 equations to choose from, and I can use either one of my very useful equations for displacement with constant uniform acceleration. And either way, try them both. Plug the values in and prove it to yourself that you get the same answer. But either way, I get the answer of 422.5 meters for my value for the displacement. Well, that's not enough for my plane to take off. So hopefully you never find yourself in that situation. Now here is our final equation that we're going to look at, I promise, in this video. What if we don't know the time interval? That could be a problem. I'm going to show you a way that we can substitute some things around and get this very useful equation. So I'm going to start with these 2 equations. I know I have my final velocity equation, but it has time in it, and I don't know the time. So how am I going to fix that? I can use this other equation right here that has a time variable in it. If I can isolate this time variable and set it equal to all of these things, after I do a little algebra, I can substitute all of these things into this equation and come up with an equation that doesn't have a time variable in it. First, I will multiply by both sides by 2. Then these 2 terms cancel. Next, I will divide both sides by VI plus VF. That's one big term altogether. And then these cancel. And I'm left with delta T on one side. Now I have this equation. I have a delta T equals all of this. If I take all of this, right here, this term, and I substitute it into this delta T, then I get what follows. Here's my new equation in terms of final velocity. If I subtract VI from both sides, I can do away with those terms on the right. Next, I can multiply both sides by final velocity plus initial velocity. I'm essentially just trying to consolidate, well, not on this side, but on this side, these terms, so that I will end up with velocity squared and a velocity squared. And I'll show you how that works. And then the nice thing about this, multiplying by this on the top and this one on the bottom, those two terms cancel. Right now, I have this equation. I'm simply going to subtract the VI squared from both sides, and when I do this, I get this equation. And here is the equation for that. Actually, I made a little mistake here. This should be minus VI squared, so I should add VI squared to both sides. I get this equation, which is the same as this. I just flipped these two terms around on the right side. And I get my final velocity squared equals initial velocity squared plus 2 times acceleration times the change in position. And that's a simple way to, other than the fact that you have to plow through some of the little algebra there, a simple way to derive this very useful equation if we don't know the time interval. So let's look at an example. Let's say you were going to push your friend in a grocery cart down an empty aisle in the grocery store. Danger. Do not try this at home. I'm not advocating that you try this, but let's just pretend you're doing that. And your friend is sitting in the shopping cart, starting from a rest position. You push your friend, who uniformly accelerates at a rate of 0.600 meters per second squared. What would their velocity be after traveling 5.0 meters? Well, let's write down the things I know. I do know my initial velocity is 0 meters per second because my friend is, their initial velocity is 0 meters per second. They're starting at rest. I know that their constant uniform acceleration is 0.600 meters per second squared. I know their change in position is 5.0 meters. And I would like to know their final velocity. So what formula do you think I will use? Well, if this is the one you picked, you're right. I don't have a time interval. I don't know my time. So this very useful formula is the one that would be most useful to me right now. So let's fill these values in. I know that my initial velocity is going to be 0 right there. My acceleration will go here. My change in position will go here, and I will go ahead and do the calculations. Now, when I plug these values in, this is a 0 term, so it doesn't matter. 2 times the 0.6 times the 5 gives me 6.00, and my units here, you'll see meters times meters. I have meters squared per second squared. Isn't that strange? Well, if you look at the formula, its final velocity squared equals this. So the next thing I need to do is take the square root of both sides. So if my final velocity squared equals this, I need to take the square root of that and the square root of that side. That will give me my final velocity. And when I take the square root of 6, I get 2.4. And the square root of meters squared is just meters. The square root of seconds squared, the per second squared is just seconds. And now I have my answer in meters per second, which is what I want. I want the velocity in meters per second, and it's 2.4. And that is my final velocity after my friend, that is my friend's final velocity after they have traveled 5 meters. Don't forget sig figs. This is the correct number of sig figs because I'm limited by 2 sig figs right there. So remember, you can obtain all of these formulas from just simple definitions. I've shown you some fancy formulas, but they were all derived from these 3 facts right here. Just remember your average velocity is change in position over change in time. Remember the average acceleration is just change in velocity over change in time. And you know that each of those terms is just the final minus the initial to find that change in. You know how to find an average of something. If you have these 3 things under your belt, you can actually derive all of those very useful formulas that I gave you. So don't be afraid of using all of them and rearranging algebraically just to suit your needs and do what you want to do in the problem that you're working on. These are all just tools for you and to use at your disposal in the ways that work in order to solve the problem. Here's an advanced idea for you, and I look forward to seeing you in class.